Okay. So I'll talk about graphes parcimonieux utilisant des mesures aléatoires échangeables. Okay. We need to remember this one. So this is joint work with Emily Fox at University of Washington. So there has been a tremendous interest over recent years in the study, the understanding, and the modeling of complex networks. So I'd be interested in different types of networks. For example, so networks, you've got a set of nodes, of vertices with connection between them that may be directed or undirected. So for example, you've got directed multigraphs. So nodes may correspond to people and an edge from one node to another node may correspond, for example, to an email from one person to another person. So you have other examples, for example, citations or the World Wide Web. We'd be also interested in simple graphs. So now you just have nodes and undirected connection between two nodes. So the most popular example is a social network. So a node may correspond to an individual and an edge to a connection between two individuals. So here, to represent the network, so the size of the node is proportional to the degree of that node, so to the number of connection of that node. And actually, so this network is a network of collaborations between Oxford and Warwick academics. So you've got Oxford in blue and Warwick in red. So as Jim mentioned, so we expect to have much more edges in the near future. So I didn't want it to put names on the graph because usually I please one person with the largest node and then I upset everyone else. So.
Definitely need a quadratic discriminant.
So I'd be also interested in the last type of network, so bipartite graphs, so where now you've got two different types of nodes, so nodes of type A and nodes of type B, and you only allow connections between nodes of different types. So for example, here scientists authoring papers, readers reading books, internet users posting messages on forums, or if you think about recommender systems, so customers buying items. So what I'm interested in in developing a statistical network model. And so why do I want to do that? So I may be interested in basically observing a network and trying to find interpretable structure in the network. So by building the statistical model, I've got some parameter that I'm able to interpret and then tell me something about the networks. For example, some block structure, some latent parameter that may explain the connectivity of that graph. I may be interested more in predictions. So, for example, I may be interested in predicting missing edges in the network, or I may be interested in predicting the connection of new nodes. So if you think about the customer buying items, so I've observed some a subset of the customer having bought some sort of items, and then I've got a new customer, and I may want to predict his set of connection. So we've got now some massive networks which has a massive size. So I've just put like latest estimate, I think, from various companies. For example, LinkedIn, so 300 million users. Facebook claims more than 1 billion. Twitter, 300 million, and the World Wide Web, so 1 billion. So we've got very, very large network, and so we've got sort of two aims. So first, so we want models that are able to capture the large-scale properties of networks, and so I'll discuss that in a minute. And we also want, once we've defined this model, we want also a scalable inference algorithm to learn the parameters of those models. And so in terms of property in this talk, so I will focus on the following property, so which is a asymptotic property of network, so which is sparsity. So what is the definition of sparsity? So if I write so NE, so think about from now think about a simple graph. N is the number of edges in the network, and N is the number of nodes. So we call a graph dense if the number of edges scales quadratically with the number of nodes. So it grows basically at the same rate as the maximum number of connection. And what I will call sparse, so there may be different definition of a sparse graph, but what I will call a sparse graph is basically a graph which is not dense. Okay, so where the number of edges grows subquadratically with the number of nodes. So it is regularly admitted that most of the real-world network are actually sparse and are not dense. Okay, so this is not because the size of Facebook doubled that the number of your friends will double at the same time. And so what comes with sparsity, what is related, is also a very heavy-tailed degree distribution. So the degree of a node is the number of connections of that node. And for many of the real-world networks, so the degree distribution are heavy-tailed. So whether or not it's a power law, it's actually a power law distribution. There's some matter of debate, but actually, anyway, it's very heavy-tailed. And what you expect also in real-world networks, so is having some sort of a latent structure, so some block structure where you're more likely to have more connection between nodes of a certain type than between nodes of different types. So I would like to be able to build a statistical network model that can capture those properties. Okay, so just as an illustration, so here's an example of a bipartite graph. So two types of nodes. So one set of nodes is the readers. So this is from the book crossing community network. So we've got 5,000 readers represented at the top. And I've got, so the second type of nodes are books. So I've got 36,000 books represented at the bottom. And so again, like as the previous picture, so the size of the node is proportional to the degree of that node. So on the top, the larger nodes correspond to readers who have read a lot of books. And at the bottom, so larger nodes correspond to books read by a lot of readers. So what you see here, so I don't know if you know some of the books, Wild Animals, Da Vinci Code. Yeah. So those are the most popular books in the data set. So what you see, obviously, so the graph is quite sparse with only a fraction of the potential possible connections. And there's a high variance in the degree of the nodes, so for both the readers and the books. So some of the readers have a very, very high degree, but most of the readers actually have only read one or two books, and the same for the books. And so if you represent the degree distribution, so the distribution of the connection for both for the readers and for the books, and you represent it on a log-log scale. Okay, so here I've got the proportion of readers having read one book, two books, etc. And here the same, so proportion of books have been read by one reader, two readers, etc. So you've got this sort of a linear trend, so indicating some sort of heavy-tail power law degree distribution. So I would like to be able to build a model that can capture such behavior. Okay, so I talked now about network modeling and the classical approach to network modeling, and I'll focus now on simple graphs. Okay, so I don't have any direction, so undirected graph without self-loops. And so typically, so we're interested in defining the model for the adjacency matrix. So where with entries, binary entries xij. Where xij indicate if there's a connection between node I and node j. And so a reasonable assumption which is made is an assumption of joint exchangeability. So intuitively, it just means that when you define your statistical model, the way you order the nodes does not have any sort of importance. So mathematically, what you assume is that the distribution of this infinite matrix Xij is invariant over permutation, joint permutation of the rows and the column. Okay, so if you apply any permutation of the node, you obtain the same distribution. So interestingly, so there's some representation theorem by Aldous and Hoover. So it takes the following form for exchangeable binary matrices. So if you make this exchangeability assumption, then you've got this representation for the matrix. So you've got Xij given some uniform random variable ui uj and some function w from the unit square 2, 0, 1. So Xij is just drawn from a Bernoulli distribution with the probability of connection w of ui uj. Okay, so there's some function, which is called in the literature the graphon. And so Xij, given this function and given uniform variable, is just Bernoulli distributed with probability of connection given by w of ui uj. And so as noted in a recent review by Orbans and Roy, so you've got several network models or Bayesian version of the network model that fit into these frameworks. For example, the Erdos-Shreni stochastic block models, mixed membership stochastic block models, a Bayesian non-parametric version of stochastic block model, etc. So that's fine. So those models can capture a lot of structure within the network. Okay. So, however, there's one limitation, which is that if you make this exchangeability assumption, then you've got one consequence, which is that graphs that are represented by an exchangeable matrix, they are either so trivially empty or they are dense. Okay, so either you've got the empty graph or you obtain a necessarily dense graph. And so to quote the recent survey paper of Orbans and Royce, who made this remark, so the theory clarifies the limitation of exchangeable models. So it shows, for example, that most Bayesian models of network data are inherently misspecified. So misspecified in the sense that they necessarily lead to dense graph, and we believe that most of the real-world graphs are actually sparse. So how can we handle this then? So some people, what do people in the literature do? So of course, so you can still work with your adjacency matrix and just give up infinite exchangeability, because if you have infinite exchangeability, then you've got densities. For example, you can work with non-exchangeable generative models, such as the Barabasi-Albert preferential attachment model, so which is some sort of a reinforced Urn process. You can also, what people do, so in the frequentist literature, is to use, to consider sequences of finitely exchangeable models, Xij of n. So maybe the most common is to use some sort of a sparsification of the graphon. So you now assume that for sample size n, your Xij of n are drawn from a Bernoulli distribution. So where the probability of connection is this graphon W of ui uj times some scaling parameter rho n, where this rho n goes to 0 as n goes to infinity. And so by doing that, you obtain sequences of graphs which are actually sparse. So the limitation of using that, so now you've got sequences of models. So those models are finitely exchangeable, but they are not consistent under marginalization. Okay, so it does not define a proper generative network model. So if you're interested in making prediction, what is the distribution of a connection of a new node given the previous one? So you cannot. It doesn't really make sense to use this. So the approach we propose is different. So we don't use this. We don't define a model on this structure, so on the matrix. So now what we will do, so we use a different representation for the graph. So we will represent the graph as a marked point process on the plane. And so what is interesting is that we've got sort of the similar properties as in the Aldous-Hoover framework. So in particular, there's also a representation theorem in this for this point process. So there's a representation by Caron for jointly exchangeable point processes on the plane, and our construction fits in this framework. So we've got some construction based on completely random measures and with the following properties. So we've got exchangeability in this point process setting. We can have, depending on the values of the parameter, we can generate graphs that are sparse or dense with heavy tail degree distribution. And an interesting point is that so the model we define, so we can derive scalable inference algorithms. So how do we represent the graph? So I represent it as a point process on the plane. Okay, so I assume that each node has some location theta I. Okay, theta I in R plus, and there's a point at location theta I, theta j if there's a connection between I and j. Okay, so here this represents a set of connection with this node theta I connected to this node theta j. And so for the moment, so you don't really need to care about the location actually. So the connectivity will be actually independent of the location of the nodes. And I won't try to learn those locations. So what is the definition of exchangeability for this process? So basically, if I take any regular grid on the plane of length h, basically, and I count the number of points within each box, so it gives me an infinite dimensional matrix. Then this infinite dimensional matrix has to be exchangeable in the previous as in the previous definition. Okay, so if I do any joint permutation of the rows and the column, I need to have the same distribution. It has to be invariant, and this has to be valid for any value of little h. So as I said before, so if I make this assumption. If I've got this assumption of joint exchangeability, I also have some representation theorem due to Caron. Okay, so now I'll describe, so this is how the process will be represented. So I will have these properties, and so now I will describe what is the network model. How do I generate a network? So as I've said, so we'll assume that the nodes, they are embedded at some location theta I in R plus. So don't really bother about those locations. I won't try to learn them, and they do not tune the connectivity. And so I will assume that each node has some sociability parameter Wi. So the larger this parameter, the more likely the node is to connect to other nodes. And the way I will generate so those Wi theta I, so I will assume that those Wi theta I, they arise from a completely random measure. So basically, you've got a pure jump here, a point process. So where the Levy measure nu of dw d theta, so is decomposes as some Levy measure that will tune the jumps, and another part that will just tune the location of the nodes. So here lambda is just the Lebesgue measure. Okay, so the important part is rho here that will tune the distribution here on those sociability parameters. And there are so two important cases to distinguish. So the first one is when the integral from 0 to infinity of rho of dw is infinite. Then we say it's an infinite activity, completely random measure. So in any interval, you will have an infinite number of jumps. And if this is bounded, then you will have almost surely a finite number of jumps in any interval 0t. So if I think about my network model, so I will have basically two cases. So I observe a graph, a set of connections, okay? And so in the first case, basically, I have an infinite population of Everyone has his own sociability parameter, but only a finite number of them have a sociability parameter that is large enough so that they actually connect to anyone. Okay. So I have only a finite number of people who have connected to someone, and an infinite number of the others have no connections at all. And in the second case, I will have a finite population. So what we will see that actually this difference between finite and infinite activity will translate into a sparsity and density of the resulting network. Okay, so this is so each node has some location theta I, some sociability parameter wi, and the way I construct the network is just the following. So the probability that there's a connection between node I and node j is just, so if I is different from j, is 1 minus exponential minus 2 wi wj. Okay, so the larger wi or wj, the larger the probability of connection between two nodes. And so I've represented here the process so graphically. So here I've represented w, okay, so with the jumps that represent the sociability of the different nodes. And so those two individuals so will connect with probability 1 minus exponential minus 2, so wi times wj. And I've got a connection at this point. Okay, so remember, if my completely random measure is infinite activity, I may have here an infinite number of jumps over any interval. Okay, so this is the model. So now I'm interested in the properties of that model. And so I defined the model on the plane. And so how will I grow the size of the network? So basically, if you look at any box here, 0 alpha square, you have almost surely a finite number of connections, okay, even if you have an infinite number of jumps. And so basically, the size of the network increases when I increase the size of this window 0 alpha square. And so I've represented, so at the bottom, this is my point process, represented the set of connection. And so here I've represented, so the n alpha, the number of nodes, depending on alpha, and n alpha e, the number of edges. Okay, so n alpha and n alpha e. So as I increase the size here of this window, so I increase the value of the number of nodes and number of edges. And so I've got here two counting processes. And so now, I'm interested in what is the behavior as alpha tends to infinity of n alpha e, of the number of edges corresponding to the number of nodes. And so interestingly, so if you assume that so rho that use the distribution over the jumps is non-zero, and you have got some basically that the expected value of the sum of the sociability parameter over any interval is bounded, then you've got the following result, so that the number of edges scale quadratically with the number of nodes if I've got a finite activity completely random measure, and it scale subquadratically, so I've got a sparse graph if W is infinite activity. Okay, so in a sense, if you use a sort of a Bayesian non-parametric model, where you've got an underlying infinite number of parameters, you're in the sparse regime. Otherwise, you're in the dense regime. And so, yeah. So to make it slightly more precise, so if I can take, so what I use for the experiment is the generalized gamma process, so where you got two parameters sigma and the parameter tau here. So this is the Levy intensity. And this parameter sigma in particular is the most important. So it can take the range between -infinity and 1. And this process so is infinite activity for sigma greater or equal to 0. And so you obtain basically the whole range of behavior. So for sigma greater or equal to 0, you obtain a sparse graph. And the graph becomes sparser as sigma increases. And you obtain dense graph when sigma is below 0. So interestingly, for this class of processes, so you can sample exactly the graph via some Huon process, and you obtain also a power law degree distribution for sigma strictly positive. So here are just some simulation from the model. So on the top left is the just for comparison, Erdos-Shreni graph with 1,000 nodes and probability of connection of 0.05. So where you obtain some sort of a dense graph. And here's a simulation from the model. So here for a gamma process, so when sigma is equal to 0, and here you increase the value of sigma. Sigma is equal to 0.5, 0.8. So as you increase the value of sigma, you obtain graphs that are sparser and sparser and with heavier tail degree distribution. Okay. And if you look at now at the degree distribution, for sigma strictly positive, you obtain those power law degree distribution. So you can look at those three curves here, the red curves that correspond to a generalized gamma process with sigma is equal to 0.2, 0.5, 0.8. So this is the same type of picture as I've shown before. So on the log-log plot, the degree distribution. And so basically the value of sigma will tune the exponent of the power law degree distribution. So the exponent being higher as you increase the value of sigma. And the parameter tau is also interpretable. It will tune the cutoff in the tails of the degree distribution. Okay, and so this is a simulation from the model. So we start from the upper left corner, and so here I'm just generating from the model on the left, and on the right, so I represent the associated graph. Okay, so here I've got the sociability parameters, the set of connectivity, and so there will be a hub appearing at some point with a high oh, it's already there. Oh, there's another one. Okay, and so this is so generated from with a generalized gamma process with sigma, which is strictly positive, so you obtain a sparsely connected graph. Okay, so it was for the model and its property. So now what do we want to do with that? So if we want to make inference, so what do I observe? So I just observe, obviously, a set of connections between individuals. I don't observe location. And what I want to learn, so I want to learn the sociability of each of the individuals for which I've observed at least one connection. And so I may, as I've said, I may have an infinite population of individuals with no connection at all. And so I want to learn W star, which is the sum of their sociabilities. Okay? So I want to learn the sociability of the person for which I've observed connection, the sociability of all the rest, and some set of parameters. So in particular, so alpha, which tunes roughly the size of the network, sigma, which will tune the sparsity, and this parameter tau that is some exponential cutoff. And so the way we derive the sampler, so we introduce a set of latent count variable, so one for each edge. And we derive a three-step Markov chain Monte Carlo sampler. So where in the first step, so we update the weights, the sociability weights given the rise using a Hamiltonian Monte Carlo. Then we update the total mass, so this is just a scalar, and the hyperparameters using Metropolis Hastings. And then we update the latent counts. Given the rise, it's just using a truncated Poisson. So the two bottlenecks are 1 and 3. And actually, those steps can be implemented very efficiently. So here you've got the gradient is very cheap to compute. And so here are some illustrations. So I simulated a graph with this set of parameters, and I obtained a network with 14,000 nodes and 76,000 edges. And so I run MCMC sampler, so with 3 chains and 40,000 iterations. And just to say that it scales relatively well, so here it takes just 10 minutes on standard desktop with MATLAB and with not a lot of engineering. And so here are some sort of trace plot for the parameter alpha, parameter sigma, tau, and the sum of the sociability parameters for all the other nodes, so showing that we managed to recover quite well the unknown parameters. And so here are some posterior credible interval for the nodes. So on the left, it's the node with the top 50 with the highest degrees, okay, and on the right, the nodes with the lowest degree. So because the graph is actually power law, all of those nodes have degree 1. And so here is on the log scale, so just to show that we managed to get quite accurately those credible intervals. So both for the high degree nodes and for the low degree nodes. Okay, so we use this model to try to assess the sparsity of real-world networks. So what we do, so we use our generalized gamma process, and we learn this parameter sigma, and we report the probability that this parameter sigma is greater or equal to 0. So based on a set of observed connections, and we do that for 12 different networks, so where the number of nodes ranges from 1,000 to 300,000 nodes, and up to 1 million edges. So here just example. So I don't think I've got. So there's the largest is the set of the World Wide Web connection. You've got internet routers, the Enron email dataset, etc. So there's a large variety of networks. So just to say that in terms of time, so it's very, very quick for the lowest for the small networks. So it takes 1, 2, up to 10 minutes for 30,000 nodes, and here 2 hours for the largest network. And so we report here the probability that sigma, that the sparse is graph under the model, and some credible intervals here for sigma. So what we identify, so we identify sparsity for, so we identify that some of the networks are dense. So for example, this one is a small social network, so you expect that it's quite densely connected. This one is a network of political blogs in the US, so again, you expect that there are a lot of connections. There's for others, so you obtain clear sparsities, for example, for the Enron data set, and here for the World Wide Web data set. So we've got quite surprising results, for example, for the internet network, where we obtain a sigma between minus 0.2, minus 0.17. So here clearly, so the internet network is believed to be sparse. So there must be some misspecification in our model and we cannot really capture this network. Okay, so I've presented a new class of statistical network model that builds on exchangeable random measure, so that can capture sparsity power properties. for which we derive a scalable inference algorithms. So at the moment, the model is very, in a sense, is very simple. It only captures sparsity because you only have one parameter that tunes the sociability of a node. So what I currently want to do is to extend, so within this framework, to extend to more structured models, so using some sort of non-negative factorization, block model version of this class of model, introducing covariate dynamic networks, etc. So here is the plot of a preliminary work on now introducing, you don't have a single parameter that tunes sociability, but you would have a set of 3 parameters representing maybe your interest in 3 different categories, etc. And so you could model some sort of a block structure in the network. So the code is available online if you want to try it. Thank you.
Thank you. Okay, we're running a bit late, but has anybody got any questions here? I mean, one thing that I personally was sort of interested in here was the fact that the way that you're setting this up, that you have this redundant theta there. And that looks really quite an interesting parameter, in fact. If you've got some sort of metric there, you can sort of start scaling up. So if you've got the units being, you know, if I get a secretary to do an order for me most of the time, if it was a computer part, right? So there would be a sort of, you could build into these systems something which actually had another process which was associated with clustering the Poisson type process stuff that you've got there, which has a completely different interpretation in terms of scaling up, which might, I mean, I think that would be quite interesting to see if you were able to do. It didn't look as if it would be too hard to do that within the framework that you've got.
Yeah, one direction we wanted to have is to introduce covariate would be to make now the sociability dependent on the location. So the location would be a set of covariates. And,
so